Hello, and welcome to the OpenBrIM platform. In this video, we give the assistant a more complex task frequently seen in real projects: the complete modeling of a bridge whose deck edges are defined separately from the main alignment. In the command, we ask it to create a single Steel I-Girder Bridge between stations 222,800 and 223,700 using the alignment files in the folder. It will use the main alignment as the baseline and the deck edge alignments to define the deck geometry. It will build the bridge's superstructure, substructure, and foundations, using Hammerhead substructures at all piers. No analysis or design is requested at this stage. We ask that the span arrangement, girder spacing, plate girder dimensions, bracing and crossframe spacing, pier cap and column dimensions, and footing and pile design be determined according to typical U.S. practice and the general rules of AASHTO LRFD 9th edition. The assistant creates the project and imports the three alignments. The first technical subtlety here is resolving the geometric relationship between the main alignment and the deck edges. The assistant determines from the files that the deck is offset approximately 165 to 235 feet to the left of the main alignment and is 70 feet wide. Because the deck is offset, the girders, bearings, and piers do not initially fall beneath the deck. The assistant recognizes this and shifts all support lines transversely to center the components beneath the actual deck, snapping the barriers to the deck edges. The superstructure is built according to AASHTO LRFD proportions: 5 continuous spans, 8 plate girders at 9 feet spacing, and code-proportioned sections. Hammerhead piers are then generated at the 6 support lines, with pile-supported footings beneath each column. The main point we wish to highlight is that the assistant resolves 2 real issues encountered during the process on its own. The first is column orientation. The assistant notices that the 24 feet wide face of the columns runs along the bridge axis and overhangs the cap and footing. It verifies this numerically and rotates all 6 columns 90 degrees so that the wide face is oriented transversely. The second is the roadway surface. The assistant detects that the roadway is still positioned on the main alignment, approximately 200 feet away from the deck. To isolate the problem, it hides the roadway and re-renders, diagnoses the source, and eliminates the visualization artifact by redefining the geometry with numeric values. As a result, the roadway, with its lane striping, is correctly placed between the barriers along the bridge. After both corrections, the assistant performs the final validation, and the model comes out clean: a complete Steel I-Girder Bridge, positioned according to the offset deck geometry, with preliminary dimensioning compliant with AASHTO LRFD. This section shows that the assistant does not merely produce geometry. It inspects the model, recognizes conditions that are erroneous from an engineering standpoint, and corrects them through numerical verification. This example demonstrates that the assistant is capable of resolving complex, real-world geometric challenges on its own, going beyond simple command execution to verify and correct the model with engineering judgment.